So in the last problem we have seen that you have to get the value of x and minus x raised to minus half and substitute in the given problem. So we have to do some simplification so that the PDE will be independent of x and y. So you will get the entire PDE in terms of W and their derivatives, and RQ may be there but X or Y should not be there. So you can see that after doing some simplification we will arrive at here. So this is the general form, this is a canonical form. So here you can see that it contains only WRQ. The canonical form of a hyperbolic PDE contains only WRQ. WRR and WQQ are not present here. So this is the required canonical form. Now we will see example 3.8. So consider the equation uxx minus 2 sin x uxy minus cos square x uyy minus cos x uy equal to 0. Find a coordinate system s equal to s of xy, t equal to t of xy that transforms the equation into its canonical form. Show that in this coordinate system the equation has the form wst equal to 0 and find the general solution. So here we have to transform the coordinate xy into st, and we have to write the corresponding canonical form. So it will have only wst equal to 0. We have to show that it is in this form, and then we have to solve the PDE also. We have to find its general solution. So when we compare, you can see that here a is 1, 2b is minus 2 sin x, and c is minus cos square x. So when we do b square minus ac, we see that b square minus ac is 4 sin square x plus cos square x, and we know sin square x plus cos square x is 1, so we will get it as 1 plus 3 sin square x, and since sin square x is always positive, we will get this quantity is positive. Hence the given PDE is parabolic. Now we have to write the characteristic equation. So the characteristic equations are given by dy by dx equal to b plus or minus root of b square minus ac by a. So we have to substitute the value of a, b and c. We have to simplify it. Again we found that dy by dx we are getting as minus sin x plus or minus 1. So we have dy by dx equal to 1 minus sin x as a 1 ODE, and another one is dy by dx equal to minus 1 minus sin x. Now we have to solve this characteristic equation. So again we can do direct integration here. So we have y minus x minus cos x equal to c1 and y plus x minus cos x equal to c2. This is our theta and eta. So in this problem, instead of theta and eta we have s and t. So we denote one of them by s and another by t. So there is no problem whichever you can choose. Okay, there is no restriction. So I am taking here s as y minus x minus cos x and t as y plus x minus cos x. Now we have to find the derivatives sx, sy and tx, ty corresponding to the new coordinate. So it is easy to compute. We have sx is minus 1 plus sin x, sy is 1, tx is 1 plus sin x, and ty is equal to 1. Now we define w to be a function of s and t. Let w equal to u of xy. So w is same as u. The only thing is that u is a function of x and y. When we change the coordinate xy to st, we represent u as w. Okay, so similarly you can write ux. So ux is ws sx plus w2 tx. Substitute for sx and tx and write it in the simplified form. Similarly we can write uy. Uy is ws sy plus w2 ty. So sy and ty are 1. So we have this uy, again we can do uyy. So differentiate uy again with respect to y. So here you have to use the product rule. So again now we have to find uxx also. So uxx is differentiate ux with respect to x. So we have uxx, again we have to use product rule here and do some simplifications. So once we get uxx, uyy and all other terms, we have to substitute it in the given PDE. Substitute in the given problem and simplify it. So we can see that so many terms get cancelled. And substituting in these equations, we will get minus 2 sine square x wst minus 2 cos square x wst is equal to 0. So again simplifying, we can see that it is minus 4 wst equal to 0, which implies wst equal to 0. So this is the required canonical form. So we have found the canonical form. Now we need to solve it. So we have wst equal to 0. Now if we integrate this, we can solve this canonical form. So first we have to integrate it with respect to t. So when we integrate with respect to t, you have to consider s as a constant. So when you integrate it with respect to t, we will get ws is equal to a constant. So that constant can be a function of s. So we have ws is equal to a function of s. Now again integrate with respect to s. Okay, so when you integrate with respect to s, integrate with respect to s, we see that w is equal to integral f of s ds plus a constant. That constant can be a function of t. So it is w equal to integral f of s ds plus g of t. Now integral f of s ds is again a function of s. So I can write it as capital F of s. Okay. So w is equal to f of s plus g of t. Now we can resubstitute for s and t. So it is our s is y minus x minus cos x and t is y plus x minus cos x. So we get the solution is u is equal to f of y minus x minus cos x plus g of y plus x minus cos x. So this is the general solution of this second order PDE. So first we have converted the coordinate system from xy to, we have converted the coordinate system to sy to ts, and then we obtain the canonical form. We obtain the canonical form as wst equal to 0. Then we integrate it. So when we integrate it twice, we get the solution. So the solution u is equal to a function of y minus x minus cos x plus g of y plus x minus cos x. So in this way we can solve the second order PDE.